Hello everyone. We have been talking about polynomial interpolation in the last few lectures. So let's try to recap what we have been doing. So the idea was very simple, that we have this x and we have this f of x, and we didn't know f of x exactly, but what we knew is some points in this curve. So some points from this curve. So these were called nodes. So this was x0, x1, x2, x3. You can give them arbitrary names if you want. And then the goal was to find a polynomial that actually goes through these points. Okay, and we had some conditions, and we also saw that if we have n plus 1 nodes, that will imply that my polynomial is Pn, that is an degree n polynomial. All right, and to find this degree n polynomial, we have to calculate n plus 1 coefs, that means coefficients, and these coefficients were found by using the condition that the value of the function at these nodes are equal to the value of the polynomial. All right, so and what we saw is that we had to solve a van der Waals matrix when we impose this condition, and either by finding an inverse or by solving by Gaussian elimination, we can solve a matrix. But it's not a very elegant thing to solve a matrix. To solve a matrix, a set of equations with Gaussian elimination or calculating the inverse when your number of nodes is really large, because it gets the computational complexity gets really high. I think if I remember correctly, it was for Gaussian elimination, it's an n-cube problem. Okay, so it's not really easy, and even if you want to calculate for 10 nodes or even more, it gets really difficult. So we have to find a new way to do it, and that is what we do in Lagrange form. Okay, but for that, what we need to know is what we have been talking about a lot is the basis of a vector space. So if you remember correctly, basis is a set of vectors that spans the space. That means that you can write any vector in that space as a linear combination of the basis elements, right? So if I give you an example of two-dimensional space Ij, where two elements of the basis set, and similarly I could use r and theta, right? So the basis was not unique, and from the number of elements of the basis we can see that this is a two-dimensional space. All right, and from there what we saw is that any vector A can be written as axi plus ayj, and similarly I could write ar plus a theta theta. So what is the difference between the two expressions? It's just that we have chosen different bases to represent the vectors. One I'm representing with I and j with the Cartesian coordinates, the other with the polar coordinates r and theta. All right, so these coefficients will not be the same, but when you add them up, the total vector is the same. They're representing the same vector, or in our case, if we change the basis, they will represent the same polynomial again. Okay, so now what is this Lagrange form? Let's see. Lagrange form. So we will choose a basis. We will choose we will choose a basis such that the basis elements will be called Lk of x. Okay, and if you remember correctly, let me give you a reminder that Pn of x, which is a polynomial of degree n, belongs to a vector space of dimension n plus 1. So the basis will have n plus 1 elements. Okay, so we will choose a basis Lk. L stands for Lagrange. We will choose a basis Lk such that Pn of x can be written as sum over k 0 to n f of xk Lk of x. So what do you see from here? This is the same as before. These are my basis elements. So these are my basis elements here, and these are the coefficients. All right, but there is a couple of things to notice here. First, let's try to expand it out. So here you go, f of x0 L0 of x plus f of x1 L1 of x up till f of xn Ln of x. All right, so what we can see from here is that we already, if I write the polynomial in this basis, we already know the coefficients because these are the values of the function at the nodes. Okay, so we have already found the coefficients, and now all we have to calculate is Li of x's. If I can calculate that, I'm done. I've found the polynomial and everything is perfect. Okay, now let's try to solve and let's try to find out Li's now. Let's see. So if I ask you what will be Pn of x0, so Pn of x0, it is the value of the polynomial at one of the nodes. So this should be equal to f of x0. This is my condition, right? This is the polynomial interpolation condition. And if you look at this form, if you look at this equation, if you look at this equation, okay, let me write it, Pn of x. If you look at this equation, then you can see that when you put whenever you put x0 here, you want the first term to go to 1 and all the rest of the terms to 0, right? Only then you can get f of x0 out of here. So that implies that this implies that L0 of x0 is equal to 1 and L1 of x0 is equal to 0, and so on and so forth. All the rest are zeros. Okay, similarly, if you apply Pn of x1, this should be equal to f of x1. Then you can say that L1 of x1 is equal to 1, and all the rest, for example, L0 of x1 is equal to 0 and everything else is 0. And everything else is 0. Okay, so we can see a pattern from here. These are the conditions. These are the conditions of our polynomial interpolation. We found the van der Monde matrix in the same way, and now what we are doing, we are trying to write it in a different basis, and we have found some properties of the basis elements, right? So now let me give you some basic algebra reminder. That is, if f of x is equal to 0 at, let's say 5. So that means that f of 5 is equal to 0. Okay, then I can say that f of x is proportional to x minus 5, right? So which implies that I can write f of x is equal to some constant k times x minus 5. So similarly, if both f of 5 is equal to 0 and f of 8 is equal to 0, let's say, then I can write f of x is equal to k x minus 5 x minus 8. All right, so now let's check L0 of x. L0 of x is equal to 0 at x1 up till xn, right? Because it's only 1 when x0, L0, I mean x0 is equal to x is equal to x0. All right, so what I can say that L0 of x is proportional to x minus x1, x minus x2 up till x minus xn. All right, but I have one more condition. What is that? That is, I know that L0 of x0 should be equal to 1. So if I want L0 of x0 to be equal to 1, then I can set this proportionality constant, because I can say that this is equal to k times this, and using this condition you can easily see that L0x is, looks like this. The terms here, the numerator stays there, and for L0 of x0 to be equal to 1, we can set this x0 minus x1, x0 minus x2 up till x0 minus xn. You can easily check whenever you put x0 here, we'll put a x0 here, x0 here, x0 here, and all these will cancel pairwise and you'll just get 1. Okay, so now we can see a general pattern. So let's try to write them down. Let's say L0 of x will be x minus x1. I will not write x0 because it cannot be 0 at x0. X minus x2 up till x minus xn divided by x0 minus x1, x0 minus x2 up till x0 minus xn. Okay, similarly for L1 of x, so now I will have x minus x0, x minus x2 up till x minus xn, and divided by, now I have to cancel pairwise again, so it should be x1 minus x0, x1 minus x2 up till x1 minus xn. Now you can see that all the conditions are satisfied, and it goes on. Okay, I think it's clear to you, and we can write it in a general form. Lk of x is equal to product of j is not equal to 0, j is not equal to k, to n, x minus xj, xk minus xj. Okay, if you expand this out, you'll exactly see these ones. All right, and what else? Let's also try to write one more property, that is Lk of xj. Xj means one of the nodes. This is equal to delta kj. So this is called the Kronecker delta symbol, which means that delta Kj is equal to 1 when k is equal to j and equal to 0 when k is not equal to j. And the name of this symbol is called Kronecker delta. Okay, so this is a shorthand notation because we have already seen that only L0 and X0 is equal to 1, L1 and X1 is equal to 1. So whenever these two indices are the same, they're equal to 1, which is exactly said here. Okay, so now I think we have found all the L's, and now we can explicitly write the polynomial very easily. Let's say, but let's see that it makes sense. Okay, so in the last video, what we saw is that we wrote P1 of x is equal to A0 plus A1x, and A0 times A1x. And what we saw from there is that we found from two, I mean, if we were given 2 points, we could find the A0 and A1. And what we found is that x1, f of x0 minus x0, f of x1 divided by x1 minus x0. This was my A0. And I had one more term, which was f of x1 minus f of x0, and you had x1 minus x0 times x. Okay, so now what we do here is that let's try to break it down and do some calculations. So the x1 divided by x1 minus x0, f of x0, minus x0 divided by x1 minus x0, f of x1, plus x divided by x1 minus x0, that is f of x1, and minus x divided by x1 minus x0, f of x0. So I have broken down all the terms here, okay, in the next line. So what we do is that if we look at the Lagrange form, we try to isolate f of x0 is here, f of x0, f of x1. So let's try to do that here in this example for a 2-point a polynomial interpolation with 2 nodes. So if you take the f of x0 as a common factor, then what you see is that x1 minus x divided by x1 minus x0. And similarly, plus what you can do is that x minus x0 divided by x1 minus x0 into f of x1. So what you can see from here is that I can take a common sign out. So it would be x minus x1 divided by x0 minus x1, f of x0, plus x minus x0, x1 minus x0, f of x1. All right, and this is nothing but my L0 of x, and this is nothing but my L1 of x, and this exactly matches with our formula here, okay, or the most general one here. So why are we doing this? Now you can see it's really easy to find the polynomial, because you can easily calculate L0, because you just need to know x0 and x1 to calculate this here. Similarly, you can easily calculate x1, L1 of x. You know this f of x0, you know this f of x1. So this is the same polynomial that we calculated with the van der Waals matrix. So we don't need to do that. So we just have to calculate these L's, which is very easy, which is just multiplying a few factors, and you just plug in this formula, you get it. Okay, so I think it is very easy, and we will work out an explicit example in the next class, in the next video, and I hope it will be clear to you. So what all we did is that we chose a basis in such a way that it's easy to calculate. So let me just give you a small recap. Is that we had this Pn of x, we had it in this basis, a1 of x plus up till dot 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 a n x to the power n. I wrote it in a basis in such a way that I had L0 of x f of x0 plus L1 of x f of x1 plus dot 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 Ln of x f of xn. And now we have a formula to calculate these L0s, L1s and Ln's. So once we have that, and for L0 we just know that we have to do it like this, x minus x1, x minus x2 up till x minus xn divided by x0 minus x1, x0 minus x2 up till x0 minus xn. So we know how to calculate all of these. It's just multiplying a few numbers with this formula and dividing it. So we know all the L's and we know these values. You just plug it in and you get the polynomial. All right, so it's just a smart choice of a basis. That's it. Okay, thank you so much. We will work out an explicit example in the next video, and I hope it will be clear to you. Thank you so much.